with Jacob Bedrosian and another part with Yu Dang and with Weiran Zhao. And we're mostly insisting on the last work with Weiran. So this is about inviscid damping. I always like starting with recalling some of the important problems in fluid mechanics. And basically all these 4 points, there were a lot of recent works in these 4 directions. One is related to stability of simple flows. The other one related to long-time dynamic appearance of some structures. Many results also dealing with the KM theory. Another kind of result about the transition between laminar and turbulent flows, and also problems related to the implicit limit, boundary layer analysis, and so on. And usually in all these kind of problems, we have nice interplay between analysis, numeric, and experiments. This is, for instance, a picture about stability of vortex. This is about the Jupiter's red spot, transition between stability and turbulence, between like a laminar flow and a turbulent flow, and like well-known boundary layer separation. Of course, today I'll be only talking about stability. This is a small plan of my talk. I'll recall the Reynolds experiment. I'll give a few results about 3D, but my talk will be only talking about 2D. I'll be talking about these 3 results with Jacob, Weiran, and Yu Dang. Okay, so this is the nice picture from the Reynolds experiment. The Reynolds experiment is to show that at high Reynolds number, a laminar equilibrium can become unstable and then transition to turbulence. However, when one looks at the linearized Navier-Stokes equation around laminar equilibrium, it appears to be stable at all Reynolds numbers. Okay. Usually to study this one, try to linearize the Navier-Stokes around the simplest kind of non-trivial flows. Like you want to get some non-trivial flow and you linearize around it. And the simplest non-trivial flow is the Quet flow. It's just the flow, this kind of flow. I mean, it will appear in the next slide. This kind of flow will be, at some point, we'll be talking about this in slightly different geometries. Okay. Now, this is the Quet flow, like if we write it in 3D. So if I perturb it, I will write my velocity as the Quet plus the perturbation, and then this will be the equation for the perturbation. And the problem of transition threshold usually is the fact that if one perturbs, so if one takes U in some space, if U is small enough related to the Reynolds number, so it's like viscosity to some power, then you get stability. But if you are bigger, then you can have possible instability. So this is usually what we call transition threshold. And there have been a lot of work on this, especially there were experiments, numerics. There are different estimates about this number. I think now at least mathematically, we know that this number is 1. There were also different works. Maybe I'll skip these two. Okay, now let me mention some of the contributions we had recently. First, I'm mentioning 3D result, even though I'm not going to talk about 3D. So this will be almost the only slide you'll see about 3D. More or less, the outcome of all this is to say that gamma is 1 for 3D. And I mean, there was a very nice recent result by Shen, Wei, and Zhang proving that it is one. That it is one even in Sobolev spaces. Like in previous result we had with Jacob and Pierre, we proved that gamma is one in some Jouvre space, but one can even push it to Sobolev space. Now, today I'll be more working, I will be more talking about the 2D problem. And if one considers the following kind of space, these are Jouvre spaces, meaning that the Fourier transform has to decay like exponential minus xc to the power s. If you take s equal 1, that corresponds to analytic regularity. So what we proved with Jacob, maybe like almost 7 years ago or more, that in 2D, for the Euler flow, if one takes small perturbation in this space, then we have so-called inviscid damping. I'll be giving a more precise result later. I mean, when we first started giving talks about this, like for me, the question I was asked were like, I can put them in 3 kinds. One of them was what happens in 3D. That's the previous slide. I mean, there were a lot of advances on 3D. But then the next question was, do we really need this funny Jouvre regularity? And actually, I have a result with you, Dang, that proves that this regularity is somehow needed, meaning that if we don't put this regularity, we have some kind of instability. The next kind of question is, what if one perturbs a more general shear flow? I mean, instead of perturbing wet flow, what if we perturb another stable shear flow? And it turns out that, okay, we are able to prove that a similar result to the one we have here also holds for stable monotone flows. This is a recent paper with Weir and Zhao, and UNESCO and Yao Jia, they have also a similar result. Okay, so let me mention also few recent results. I think there are tons of results recently, so I'm sure I'm forgetting a lot of people. I'm sorry about that. I mean, I think it's becoming difficult to keep track of all new results, but there were many results in different directions at the linear level, like some of the, like for different kind of stable flows, one can prove inviscid damping. The case of the vortex case. There were also results about what happens if one looks at the problem in Sobolev space. Okay. So-called enhanced dissipation. I'm not going to really discuss this here. Other models. Okay, so of course there is also huge literature on the plasma physics equivalent of the Euler flow, which is the Landau damping. There are also a lot of literature here. Okay, now let me state the first result with Jacob. So to state the first result, the starting point is the 2D Euler equation written in the torus times R. Okay. One can write an equivalent formulation based on the vorticity, and it's well known that any function of this type, you have u of y. I mean, there is a small abuse of notation here. I mean, u of y is 0. Any function of this type is a stationary solution of 2D Euler, and the particular case u of y equal y is a particular case, is called wet flow. And let me start by the stability of wet flow, or like the asymptotic stability of wet flow. Now, if one perturbs the wet flow, this is the new equation we get, right? So this is the new equation, meaning that here I'm writing my vorticity as equal -1. I'm writing vorticity equal -1 plus omega. So this will be the new equation for the perturbation, okay? So this equation at the linear level, it is stable, no growing modes. However, the Sommerfeld paradox, I will not really discuss it here, but it suggests that there may be some strong nonlinear effects. And also the fact that the stability may depend on the regularity. That's really the main thing here. Okay. So to state the result with Jacob, I have also to introduce the Gevrey regularity. Here I'm taking Fourier in X and Y. X is in the torus, so that's why the Fourier variable of X is in Z, whereas the Fourier variable of Y is in R. And this is the kind of space we consider Gevrey space, meaning that the Fourier transform has to decay like exponential minus k plus c to the power s. This Fourier side definition is actually equivalent to a definition on the physical side. I mean, we will not use this definition. And also S equal 1 correspond to the analytic regularity. Okay, now this is the result with Jacob. It says that, okay, just here to recall that there are two indices, lambda and S. S is the power you see here. And lambda plays the role of the radius of analyticity when you are analytic. So the result with Jacob says that if you take a perturbation which is small in this kind of spaces, then the solution will stay uniformly bounded in a space where you lose a little bit on the lambda. I mean, it's like the loss on the radius of analyticity when one considers analytic functions. But to get this, one needs to modify a little bit the coordinate system. I mean, it will be clear why we need to take this into account. I mean, even at the linear level, this is completely needed. Okay, so this is the result with Jacob. I mean, it's like 100-page paper, and it also contains asymptotic stability, meaning that your vorticity written again in the right coordinate system, will converge to some final profile. And of course, I mean, this convergence, here there is an epsilon square, the epsilon square meaning that your initial data is equal, that F infinity is equal to the initial data plus something of size epsilon square, right? So this is really like scattering theory. Okay, I mean, again, I mean, this is similar to the lambda damping in the Vlasov flow. So with you, Dan, we try to prove that this kind of regularity is actually really needed. Basically, we prove some sort of instability if one considers a Gevrey class which is below the Gevrey class 2. I mean, usually the Gevrey, what we call Gevrey class is usually 1 over S. So meaning if now I take S less than 1/2, okay, I mean, I need to recall, right? If S is less than, I mean, if S is bigger than 1/2, the space is stronger than when S is less than 1/2. Now if I take S is less than 1/2, remember in the paper with Jacob, we had to assume that S is strictly bigger than 1/2. So now if one takes S strictly less than 1/2, and for any small initial data, we can choose omega such that at a later time, capital T, the solution will be large. But unfortunately, we need it in some high Sobolev space. Will become large in high Sobolev space. Of course, one would like to be able to prove this in L2 kind spaces, but I think we are far from that. But we find that this is already a very satisfactory result. It means that the equivalent result to what we have with Jacob doesn't apply here. Also, one can actually make any change of coordinate you want. Like one may think that this is due to the change of coordinate. So one can put any change of coordinate, it will not work. One can even replace this S strictly less than 1/2 by 1/2, but then you need some smallness on lambda. And I mean, from the proof, this is kind of estimate that one has on the time you have to wait to see the instability forming. This result here is also related to other results that show that the Quet flow is not asymptotically stable in some kind of Sobolev regularities. So there was a paper of Lin and Zhang proving that in H3/2. Another paper, also papers about the Vlasov equation. Like I mentioned, the Landau damping is the equivalent of the inviscid damping. And there is a result of Jacob, which is very similar to our result. I mean, like at least the statement is one can compare the result of Jacob for Landau damping to our result for the inviscid damping. Okay, now let me try to explain a little bit, mostly at least the linear level. So at the linear level, when you linearize around Quet, the nice thing is that the linearized operator is very simple. So the linear analysis is completely, everything is explicit. And I mean, you have to understand very well what's the meaning of this. I mean, it's transport. And the nice thing is that also when you go to the Fourier side, it is also transport on the Fourier side. So what does this mean? It means that if I go to the nonlinear problem, if I make this change of coordinate, this is my equation at the nonlinear level after I make this change of coordinate. At the linear level, it will be dtf equals 0, right? At the linear level, f is just independent of time. Now, when one looks here, there's this funny Laplacian t minus 1. And I mean, this is just a small exercise of change of coordinate. The Laplacian in the xy variable, when you write it in zy, it becomes this funny operator that is time dependent. But of course, I mean, it has a feature in it. I mean, if one looks at it a little bit, even at the linear level, again, if you forget about this term, you get the fact that phi will decay like 1 over t squared. So this is really what I mean by that at the linear level. So at the linear level, my f is independent of time. And then if I apply Laplacian minus tf, Laplacian minus t meaning phi is the potential. The potential, you take this, which is the initial data, you multiply by this guy, when t goes to infinity, you get 1 over t squared decay, right? And this is the starting point really of this global stability, right? It's really what is behind the global stability. That's how we see it on the Fourier side. Of course, now the slightly drawback of this is that you have to lose derivatives if you want to prove this in a uniform way. And this kind of loss of derivative is what is behind the requirement of the Gevrey regularity. Now, that same picture, one can try to draw it on the physical side. On the physical side, think about this as being your initial data, and then you are mixing your flow with this wet flow. So when t goes to infinity, you start, like, let's say, with a perturbation like this straight, and then as time goes, it mixes, right? So this is what happens when t goes to plus infinity. This is what happens when t goes to minus infinity. And this is really, this picture means that your omega is decaying in negative Sobolev spaces. So this decay in negative Sobolev spaces, this is what now we talk about when we talk about mixing. Like a lot of literature, a lot of papers have been written recently about mixing, and usually people measure mixing by looking at the function in negative Sobolev space. That's what we mean by mixing. And that's exactly the decay we have here on the stream function. Okay. Now, another feature of this is that I said if my initial data is here, this corresponds to mixing when t goes to plus infinity. This corresponds to mixing when t goes to minus infinity. Now, if my initial data is here, what happens? If my initial data is here, then first I go through unmixing, and then I go through mixing. So meaning that my solution will grow first and then decay. And this sort of growth then decay is what we call transient growth. And it is behind a lot of it's behind what we call echoes especially in the plasma physics equivalent of this problem. This is what, okay, I don't want to go through explaining these slides, but this, I want to mention that echoes in plasma physics was observed experimentally. There are experiments trying to show that these things appear and interact. I will not go more into this. Okay, now I'm going to go to my next result, which is, again, I'm not going to talk more about the result with you, Dang, about the instability. If I have time and if people ask questions, I have a few slides about it. But I want to discuss what happens if instead of perturbing around wet flow, I perturb around a more general shear flow. Okay, so this is now the third result, which is the result with the Weir and Zhao. So now I'm going to look at my problem in the domain which is the torus times 0, 1. So x will be in the torus, but y will be in 0, 1. And I suppose that I'm perturbing around a shear flow u of y. Of course, now when you perturb around a shear flow which is not wet, you will get an extra term, an extra linear from the linear analysis, right? There is another term, which is this one. This is the nonlinear term. So again, here, let me spend few seconds to re-explain this. Omega is the perturbation, is the vorticity of the perturbation. It is associated to psi, which is the stream function. Now the stream function has to vanish on the upper and lower boundary. That what ensure the slip boundary condition, but no penetration. It ensures that the normal velocity vanishes at the upper and lower boundary. Because this is the velocity, capital U is the velocity of the perturbation, and U of y is my shear flow around which I am linearizing. Okay, so this is the linear part, this is the linear part, and this is the nonlinear part. Of course, now when one looks at this, this is no longer as simple as what we had here, right? In the case of QET, this was the linearization, and it was, you solve it like in just one line. Now, this linear problem turns out to be much, much more complicated just because of this non-local term. I mean, notice that this is a non-local term. It's true that you can think about it as some sort of compact perturbation because of gain of derivatives, but okay, one has to be careful about all aspects of spectrum. So what are the assumptions we have to impose on U? We have to impose mostly that U is stable. That's the linear stability, which is usually understood by looking at the Rayleigh operator. This is what we call the Rayleigh operator. The Rayleigh operator compared to here, there is a dx here. Like if we look at this on the Fourier side in x, dx becomes I alpha, but then your operator will be I alpha times this. So we assume that we have no eigenvalue and no embedded eigenvalue. So the other thing we have to assume is that it is monotone. And a last thing is that U double prime has to have compact support. So meaning that when you get close to the boundary, the upper and lower boundary, you have really to look like linear. You have to look at like some multiple of QET. Like there is a reason behind it. Maybe I'll explain a little bit, but it turns out that for this kind of flow, I wanted to mention that for QET, if one takes U of y here equal y, right? That's a possibility. If U of y equal y, so then this term is not there. If U of y equal y, this term is not there, but you look at the problem between 0 and 1. Ionesco and Gia, after my paper with Jacob, they also extended our paper to this case. The difficulty there is mostly to prove that the vorticities doesn't touch the boundary. You want to prove that if you start with the perturbation of the vorticity far from the boundary, stay far from the boundary. I mean, here we want to extend this to a general monotone flow. The last assumption is a Gevrey assumption. I mean, this is a very natural that one has to impose Gevrey regularity because, I mean, we'll be proving a result in Gevrey regularity. So definitely we need this to be Gevrey. Okay, now this is the result with Veyran. More or less, the result is to say same conclusion as in the paper, as in my paper with Jacob, meaning that we start with an initial perturbation, which is compactly supported away from the boundary. So you have to stay slightly away from the boundary initially. Then you prove that as time goes, you stay also away from the boundary. And we have this sort of scattering. Your omega written in your right coordinate system will converge to some final F infinity. The only small thing here is that this is epsilon. In my paper with Jacob, this was epsilon square. And there is a reason behind it. The reason behind it is that even at the linear level, I need to take into account, I need to remember that there is, one second, sorry. There is this non-local term that I have to take into account if I want to improve, to make this epsilon square. So, and this is actually part of our proof. Part of our proof is to introduce the so-called wave operator that allow us to get rid of the non-local term. So now if one applies the wave operator to omega, then we recover the epsilon square, meaning that when you take the wave operator applied to omega, it evolves as a perturbation. I mean, it evolves as a nonlinear term. Whereas clear, omega, even if you make a change of coordinate, even if you try to make a change of coordinate to get rid of this, you cannot get rid of this linear term. So you need the wave operator to get rid of this nonlinear, you need the wave operator to get rid of this linear term. Okay. Yeah, as I mentioned, UNESCO and GIA, like almost same time as our paper, they have similar result. They don't introduce the wave operator, so, but they introduce a finite quantity they call F star that also behaves as a nonlinear perturbation, basically. Okay, but I'm not sure whether one can deduce something similar to this from their result. Okay, now in this statement, which is more or less what we are going to prove, I mean, I'm not going to prove the statement as in the theorem, but more I'm going to prove this. There are two aspects here. If you look here, there is a linear analysis, which is the construction of the wave operator. So this is a completely linear difficulty. And then the second thing is the introduction of the new coordinate system. The new coordinate system is a nonlinear analysis. It's a nonlinear analysis. I mean, when I talked here I introduced a new coordinate system, which was z. Z was x minus ty. At this level, this was linear. But when you move to the nonlinear problem, you have a part of the velocity that you have to add here, right? And that part of the velocity is what is the zero mode, which is not decaying well enough. And you have to, we have to make a change of coordinate based on that. So I'll explain that. But first, before talking about the new coordinate system, let me spend some time talking about the construction of the wave operator, which is really the linear analysis. Okay, this is the linear problem written in terms of the stream function. Again, remember, if u of y was y, if I take wet, this term disappears, and then this becomes a simple transport equation. Now this term, if I move now to the Fourier side in x, this is how my equation looks like. And then if you invert, you apply Laplacian minus 1, you can write down an equation on the stream function. This is the stream function equation. It's R alpha is just the Rayleigh operator. Usually the Rayleigh operator is this one, but written in a different, instead of writing it on the vorticity, we write it on the stream function. Okay, I mean, this is the spectrum analysis of this operator. Let me go fast on this. But the point is that at the linear level, this is your equation at the linear level. right? You have this R alpha, and the spectrum of R alpha is more or less, I mean, it's a difficult question to understand the spectrum, but there is a, now there's some literature on this. And okay, now one can write a representation formula using the resolvent to solve this problem, right? This linear problem. I mean, first I want to discuss the linear decay, right? As I said, for QET, psi decays like 1 over t squared, just from a formula. Here, to get that 1 over t squared decay on the vorticity, you need more work. So first you need to write down, to use this representation formula to write down psi like this. This is some sort of contour integral. I mean, you have to go around the spectrum. Okay, I mean, psi will solve this inhomogeneous Rayleigh equation. That's how you compute C minus R alpha minus 1 of this initial data. This is your initial data. And then you can get your stream function at time t. You can represent it in terms of this psi. And this is your contour integral. You take this integral around the spectrum. I mean, the spectrum is just the range of u. Okay, now one can send epsilon to 0, and basically you get this representation formula. I mean, all what I'm talking about, this is more or less from a paper of Wei, Zhang, and Zhao, where they prove the linear inviscid damping. So again, like here one has to think about this, like even like proving the linear inviscid damping for general shear flows requires a lot of work. Like this may be like a 60-page paper to prove that psi will decay like 1 over t squared. And that decay of psi like 1 over t squared, the idea behind it is just the fact that this quantity here, you see here, has some regularity in C. So basically what you are going to do, you are going to do some integration by parts in C, right? You do some integration by parts in C, and that's how you get the decay of psi. And from there you get the decay of the two components of the velocity, V1 and V2. So V1 will decay like 1 over t, V2 will decay like 1 over t squared. This is very similar to the conclusion we had in the case of QET flow. But with the difference in the case of QET flow, everything was explicit. So I had a formula. Here, if I just use this kind of regularity, I mean, I will not get a formula. So that's, okay, I think I'm going to skip this slide because, I mean, this is more or less in the paper of Wei, Zhang, and Zhao. In our paper now, we had to find a more precise representation formula of psi. And basically to construct the so-called wave operator, I'm going to explain now. Let me mention again here, as of now, the 4 steps I talked about here was the linearization, then use spectral property to study the linear operator, that we used some ODE, some singular ODE to solve for that big psi, and the decay was coming from the regularity of that kernel. Now, to move to the nonlinear problem, we need, as I said, slightly more precise description of the solution. I mean, this is more or less the solution, but we need slightly more precise description. And the more precise description is introducing the wave operator to get rid of this non-local term. So I want to apply an operator, DUK, I mean, I'll explain it a little bit, so that I get rid of this term. So I want to conjugate my operator here to just some sort of transport equation. Usually, like for self-adjoint operator, this is a simple thing. For non-self-adjoint operator, one has to work slightly harder. But basically, what we are able to do is to construct this object. Again, this object uses more or less that representation formula from the paper of Wei, Zhang, and Zhao. So at the end, we are able to write it down. We are able to construct a wave operator that has a part which is a multiplication, and another part which is some sort of singular integral. Now, not only we construct this object, but then we have to understand what this operator is doing on the frequency side. I'll explain why we need that. Okay, now, again, I should say that the wave operator is bounded in L2, and we need to understand now how this linear analysis interact with the nonlinear proof. Now, in the paper, in my paper with Jacob, at the nonlinear level, there was, I can put our result in two pieces. There is a nonlinear change of coordinate and then a careful analysis of so-called resonances. I'm not going to talk too much about this. It turns out that the resonance is actually the main difficulty in the paper with Jacob. And the good thing is that it works the same in this case. However, like the interaction with the nonlinear change of coordinate requires this little bit of careful adaptation of the wave operator. Basically, okay, now in the paper with Jacob, we had to introduce a change of coordinate, which is the following change of coordinate. We had, I mean, there u of y was just y, but we need the same one here. I have to correct by the zero mode of the velocity, because the zero mode of the velocity, this sort of average, this is the notation for the average on the torus. This is the average on the torus. This guy doesn't decay well enough. It doesn't decay well enough. And doesn't decay. So that's why we have to correct by it, right? Like we correct by y or u of y, we have to correct also by that part of the nonlinear velocity. This is just a cutoff in y. The reason we can put cutoffs like this is because the vorticity doesn't touch the boundary, because we started away from the boundary and we want to make sure that we stay away from the boundary. Okay, need to go slightly fast to finish in 5 minutes. So now, how does this wave operator interact with this change of coordinate? It's not clear that the two things will interact well. So we had actually to reconstruct the wave operator, but that Rayleigh operator that I have to write it in the v variable, right? So, so this is my new r, but in the v variable. What I call Laplacian t here, what I call Laplacian t is just the Laplacian in the zv variable, right? So when I go to the zv variable, the Laplacian in xy becomes the Laplacian t that you see here. So we have to construct this this bold D UK, which is related to this Rayleigh operator. So basically, okay, let me write down precisely the definition I want. I want that this wave operator conjugates this R to just multiplication by V, right? So this is what at the end we want. The good thing is that, okay, after a little bit of work, it turns out that what we want to get about this wave operator is some sort of change of coordinate of this DUK that I mentioned earlier, right? So one can construct this. So again, I mean, I want to insist on one thing, that the wave operator that you see here, the linear wave operator, allows you to get rid of this non-local term, right? However, when you do the nonlinear analysis, there is another term, there is another nonlinear term that doesn't decay well enough. And the new wave operator that we have here has the advantage of also removing the part of the nonlinear term that doesn't decay well enough. That's really the advantage of it. Now, how does this now interact with the so-called resonances? That's the second part in the proof with Jacob. How does this interact with the resonances? It turns out it interacts well because it doesn't move too much frequencies in the Xi variable. And we have to prove it. I mean, the part of the paper is to prove this kind of estimate on the kernel. So it behaves well, both how it moves frequency in Xi, and then how also it commutes with multiplication by constants. As I said, it commutes well with the time derivative. It commutes well with the time derivative because of this identity that, I mean, it's not difficult to prove from the exact formula here. The last step in the proof is to introduce a norm based on the so-called toy model. This is really exactly the same norm I used with Jacob. I mean, of course, now we are going to apply this to the vorticity, but after applying the wave operator, it turns out we only need to apply this wave operator for k less than some km. For k bigger than km, for k bigger than km, it turns out that the non-local term becomes very small, so we can just absorb it. I mean, there's no need to correct in that case because of some extra smallness that we get from inverting the Laplacian there. Of course, then one has to write down, I mean, it's a lot of commutators compared to a lot of commutators that one has to study. But the good thing here is that we can use my paper with Jacob as almost a black box. So that's why we don't need to redo all the resonance analysis. We only need to study a lot of commutators to make sure that the analysis done for the wet flow can apply here too. So again, I mean, if I make a summary of this proof, there were construction of the wave operator, that was the first steps. I talked a little bit about this nonlinear change of coordinate that more or less comes from the paper with Jacob, but then we have to modify the wave operator to adapt it to that new change of coordinate. And then we have to study some commutators to make sure that the energy norm the energy norm A, this energy norm behaves well. Okay, so I think I'm going to stop here. I mean, I'm not going to talk about the other result. So thank you for your attention.